Hello everyone, welcome to the networking deep dive session. I hope you're all having a good day so far. In this session we will be looking at networking and how we're going to be putting the I into the Internet of Things. So my name is Mark Stevens. I'm a software engineer and hardware engineer based in the United Kingdom. I started writing software way back in the 1980s, and I became involved in embedded development in around about 2010 with the Arduino family of microcontrollers. I've used a number of different technologies since then, and I became involved with Wilderness Labs around about 3 years ago. I'm currently working on the network stack for both the STM32 and the ESP32 microcontrollers. So in this session, we're going to have a look at the hardware and some of the system architecture of the Meadow F7 board. We will have a demonstration of the networking in action, and we'll round off with a status update on the networking stack. So the Meadow board itself. This board has two different MCUs on the board, MCU being a microcontroller. The STM32 is responsible for running your code. This is supported by the Mono runtime system, and this itself sits on top of the Nutex real-time operating system. The companion processor, the ESP32, this provides services such as Bluetooth and Wi-Fi. These services sit on top of an application which we have written, which is run on the free RTOS system. This architecture has a couple of advantages which you won't find in any other microcontroller. The first is that the ESP32 can be turned off. So if you're gathering sensor data out in the field and you're running on battery, then you can turn the ESP32 off when you don't need it, and this enables you to extend the runtime lifespan of your battery. The second is it gives more power to your application. So the STM32 can be running your application when a Wi-Fi request, say a Wi-Fi request is made. This is offloaded onto the ESP32. The STM32 can then return to running other tasks within your application until the Wi-Fi request is completed, at which point the ESP32 would signal that a response is ready and will be passed back to your application. So let's have a look at the system. So as mentioned before, we'll start off with the STM32. This is running your application within the context of the Mono runtime system. So the .NET libraries that I've highlighted here will be part of the Mono runtime. And the Mono runtime itself also contains something called a platform abstraction layer. This platform abstraction layer acts as an interface between Mono and the underlying operating system, and the operating system in our case is Nutex. So on the other side of the equation we have the ESP32. This is connected to the STM32 via a number of hardware interfaces. So we have the UART interface, which allows us to program the ESP32. We have the SPI interface, which is used to send data between the ESP32 and the STM32, and we have a number of GPIO pins which are used for signaling and control. So on the ESP32, as mentioned before, we have the free RTOS system. This has an application which we have put together, which takes the messages from the SPI channel. It works out which of the system interfaces the message is for. So for instance, a Wi-Fi request or a Bluetooth request. It then dispatches the messages to the appropriate interface. That interface then deals with the messages, say for instance a Wi-Fi connection request to connect to an access point. The Wi-Fi request connects to the access point and then signals back to the application running on the ESP32 that we've connected In return, that goes through the GPIO and the SPI system to the STM32, so your application will get a message to say your request for connection has completed. So let's have a look at an example from your code. A possibility is a GET request using the HTTP client. So this request, you would pass on, say, the URL google.com. You would pass that down into the .NET framework. And again, remember that the .NET framework, Mono, and the platform abstraction layer are all part of the Mono runtime system. So the Mono system will process the GET request and decompose that into a number of lower level requests. So in the case of getting Google's homepage, you are looking at working out where Google is, so what its IP address is, making a connection through to the server, opening a socket, reading and writing data, and so on. So those requests will be broken down into lower level system calls, and that's the responsibility of the platform abstraction layer. So that will have in the context of a socket, that will have a method which is something like system native socket. That request deals with interpreting the data that the runtime libraries understand and breaking that down into operating system calls. And in this case, we're going to make a POSIX compliant operating system call through to NUTX. And that would look something like the socket request. So now let's have a look at a demonstration of that low-level system in action. So I'm just going to switch over to the debugger system. So on the screen now, you should see two distinct windows. The window in the left is the command window, which I'm going to use to fire up GDB to start talking to the STM32. The window on the right is a serial connection made through to the STM32 and will allow the STM32 to give us status messages through back to us as the application is running. So we start off invoking the debugger, and the application we're going to run is that simple GET request that we saw earlier in C#. We're going to get Google's homepage. So we'll set a breakpoint in the main method that's going to run all this for us. And it would help if I could spell. So we have a breakpoint in the get Google homepage method. The source window there, the source section of the screen shows the method we're in at the moment, which is the startup method for NUTX. So let's continue running the application until we get into. So right, you can see the message. Actually tell us the initialization. But we've actually so the chip isn't running, so that message will eventually get completed as we get further and further into the application. So let's just step over a few lines. And if you see in the source window, we're at line 186, and we're just going to print a message to say that we're going to initialize the network and restart the ESP32. So what I'm just going to do now is bring up a second window for you to look at. I'm going to put this on top of the debugger window. And this window is another serial console. This time it's connected through to the ESP32, and we'll get status reports from the ESP32 as we're executing the application. I'm just going to set a breakpoint on line 194, and we'll just run the application to that line. And what should now happen is the ESP32 should be reset, and we should get some messages telling us that the system's up and running. So as you can see, we've started the Wi-Fi, and if you look at the ESP32 output, it's telling us that we've got an IP address of 192.168.1.170. So we've got a good indication the Wi-Fi is up and running. If we continue this application, this will run through that lower level set of routines. So we will get an address, we will get the IP address associated with google.com. We will look, we'll make a connection to that server. We'll send a request over to the server, and then we'll pull back the result, and we should get a display of the first 100 bytes of the response from google.com. So I'm just now going to let that application continue to completion. So the window on the right is showing us the STM output and the progress. So as you can see, we've got the first 100 bytes, we've displayed those, whilst on the left hand side the ESP32 is continuing to get more and more data from Google. We've just restricted it to the first 100 bytes. So there you can see that we've got a 200 response from Google, so that's a positive response that we've got a good connection. And we pulled back 13K of data in 15 read operations. At the moment, for testing, we have those read operations restricted to 1K. That's why it took 15 operations to pull that amount of data back. So there you have it, the low-level networking as implemented at the moment. So that shows you that the STM32 has the ability to make requests through to the ESP32. We have a fault-tolerant communication between those two systems. So if we do get any data errors, we have the ability to detect them and to recover from those errors. And we also have the ability to connect through to a Wi-Fi router and to pull data back from the internet. So let's switch back to the slide deck. Okay, so the current status of the system, you've obviously seen there that the low-level methods are working. And as we discussed earlier, the Nutex system is running or presenting a set of POSIX APIs back through to the calling application, in our case the platform abstraction layer. So we've got the STM32 ESP32 request response system that's now well tested. The control of the Wi-Fi is also tested, and we also know that we've got a POSIX API within Nutex and also within the platform abstraction layer. We are going to we have the methods that you saw working earlier. They are POSIX compliant APIs. So now the piece of work that needs to be completed is to wire those two sections up. We did have a setback in April. We started having some space issues, and in resolving those issues we also encountered a linker issue. But all's not lost. The good news is that this week one of our developers has cracked the linker problem and has cracked the space problem. So we can now continue with the networking, and we can wire those two layers back together. We can now wire those two layers together. That will allow us to connect the C# classes through to the POSIX APIs, through to Nutex, and through to the ESP32. And that work is currently ongoing. And so that's where we are with networking at the moment. So in the presentation, we've had a look at the hardware in the system architecture. We've discussed the two controllers working together. We have a fault-tolerant system of communicating between the two processors, and the low-level networking, we've seen that in action. And we've had a look at the status of where we are this week, and going forward, our work is to link those two systems together, and that's currently ongoing. Thank you for your time, and I know the world is very different from what we're used to, and please, all of you, stay safe and best wishes.